Entropy is a fairly simple concept to calculate and hopefully fairly simple to predict, looking at the orderliness of a starting and an ending component. But why do we need to know about entropy in terms of chemical reactions or in terms of understanding what happens and what doesn't? The laws of thermodynamics can be stated in all sorts of different ways based upon what you're trying to explain or why. But one way to say the second law of thermodynamics is to say for a favorable process, the entropy of the universe increases. Really, the entropy of the universe is always increasing, or that is the natural flow of energy. The energy is going to be dispersed. And we've got this picture here. If left to itself, if we took these two samples, our reds and our greens, and removed that barrier, they would mix up like this. And although maybe statistically possible, they're not going to go back to this separate arrangement on their own. That is not the likely or the natural flow of energy. But if we're looking at individual reactions, and we looked at some previously, it is possible to have a negative delta S, a decrease in entropy. We can take liquids, free moving particles, and freeze them into solids. We can take gases, which are moving quickly and randomly and all over the place, and turn them into liquids or solids. We can have synthesis reactions where separate particles combine into one big thing, or we can separate our mixtures. We can take these things, if it was something like salt and water, and by physical means, or sometimes by chemical reactions, get them back separate. So although entropy naturally goes towards more random, there are ways to decrease that entropy. So we have to think about all thermodynamic factors. And when we do that, we're thinking about the two main factors. One is what we just described and talked about, entropy. How random are the particles? The other is the energy, maybe in a more classical sense, the heat or the temperature. So enthalpy is our delta H. Entropy is our delta S. And as we consider both of those together, we can think about what would happen and what might not happen. And a phrase we use a lot to describe that is thinking about which one of those, or both, and sometimes neither, drives the reaction or is favorable enough that lets this chemical process occur. So the two questions we're answering is, for this reaction or this chemical system, is heat coming in or being released? And for this same thing, is it increasing our randomness or decreasing it? A favorable flow of heat or energy are exothermic reactions. Exothermic reactions have enough energy to occur, and in fact, they occur and release energy. From a heat, enthalpy, temperature change sense, exothermic reactions are more favorable than endothermic. With endothermic, we have to have enough energy to put that in or that they can absorb it. Less favorable. From an entropy sense, we just talked about that increasing the randomness, increasing the disorder, or having a positive delta S is more favorable. So an increase in entropy is more favorable. We have a chart right here, and we don't want to memorize this chart. We want to think of it just in terms of maybe these definitions here. But what is favorable and what is not? Increasing the entropy, or taking orderly things and allowing them to become more disorderly, is favorable. So a positive delta S is more likely to be a favorable process than these negative delta S. From an energy or enthalpy sense, that negative delta H is the more favorable process. So the most favorable types of chemical and physical changes increase the entropy and release energy, positive delta S, negative delta H. No matter what, if we have a reaction that we can either calculate or predict these to be positive and negative, that would be favorable. Any reaction that is negative here and positive here requires energy and decreases the entropy is never by itself going to be favorable, or that is thermodynamically unfavorable. These other combinations, when the signs are the same, positive with positive, negative with negative, we have one component that's positive, one that's negative. So we say these could be favorable, and either the energy or the entropy would be driving the reaction. And rather than just looking at these as abstract things, we're going to look at specific ways to know exactly how favorable things are in terms of entropy and entropy or enthalpy in specific conditions.